11.9 Representations of functions as power series. In this section, we learn how to represent certain types of functions, such as sums of power series, by manipulating a geometric series, or by differentiating or integrating such a series. You might wonder why we would ever want to express a known function as a sum of infinitely many terms. We will see later that this strategy is useful for integrating functions that don't have elementary antiderivatives, for solving differential equations, and for approximating functions as polynomials. Scientists do this to simply simplify the expressions they deal with. Computer scientists do this to represent functions on calculators and computers. We start with an equation that we have seen before. Equation 1, 1 over 1 minus x equals 1 plus x squared plus x cubed plus ellipsis equals the sum from n equals 0 to infinity of x to the power n, which is, and then you have the absolute value of x is less than 1. We first encountered this equation in example 11.2.7, where we obtained it by observing that the series is a geometric series with a equals 1 and r equals x. But here our point of view is different. We now regard equation 1 as expressing the function f of x equals 1 over open 1 minus x close as a sum of a power series. Sidebar: a geometric illustration of equation 1 is shown in figure 1 because the sum of a series is the limit of the sequence of partial sums. We have 1 over 1 minus x equals the limit as n approaches infinity of s sub n of x, where s sub n of x equals 1 plus x squared plus ellipsis plus x to the power n is the nth partial sum. Notice that as n increases, s sub n of x becomes a better approximation to f of x, for negative 1 is less than x, and x is less than 1. See figure 1. F of x equals 1 over 1 minus x and some partial sums. Example 1. Express 1 over open 1 plus x squared close as the sum of a power series and find the interval of convergence. Replacing x by negative x squared in equation 1, we have 1 over 1 minus x squared plus 1 over 1 plus, restarting that. We have 1 over 1 plus x squared equals 1 over 1 minus open negative x squared close equals the sum from n equals 0 to infinity of open negative x squared close to the power n, which equals the sum from n equals 0 to infinity of open negative 1 close to the power n times x to the power 2n equals 1 over x squared plus, that equals 1 minus x squared plus x to the 4th minus x to the 6th plus x to the 8th minus and so forth. Because this is a geometric series, it converges when the absolute value of negative x squared is less than 1. That is, x squared is less than 1, or the absolute value of x is less than 1. Therefore, the interval of convergence is open negative 1 and 1 close. Of course, we could have determined the radius of convergence by applying the ratio test, but that much work is unnecessary here.